Hello again. So this is ML102. So this is machine learning under the hood. So what we're going to do is we're going to delve a little bit further into models and so on. Again, not too deep or not too technical, but a lot of people say, well, what's happening a little deeper? And so I'm going to take you one level down. And so I'm going to start with the types of machine learning. So there's different types or categories of machine learning. And right now, the major classification is 4 different types. So there's supervised learning. This is when the model learns from data with labels. So we already know what the right solution is, and the model tends to mimic that. Unsupervised learning is when the model learns from data without labels. So we do not know what the right answer is, and then the model tries to make some sense or some pattern in the data. Reinforcement learning is a type of machine learning which solves multi-step problems by maximizing a reward function. And generative AI are models that generate new content. And if you read a machine learning book before November 2022, you wouldn't have seen the 4th type. So before November 2022, most books would have told you there's 3 types of machine learning: supervised, unsupervised, and reinforcement learning. In November 2022, OpenAI released ChatGPT to the public, and of course, it caught fire. And since then, I think everything we can hear of is Gen AI. And so again, if you're reading older resources, you would not see that. Now, what the terminology that I'm going to use for the 3 classes of ML that are not Gen AI is predictive ML or classical ML. Some people call it traditional ML, or and then Gen AI. So I'm going to call them predictive ML and Gen AI. And you have to remember that AI or ML is really a set of tools. It's a toolkit that solves problems. It's a general purpose technology. Andrew Ng always says it's electricity, right? It's the new age electricity. And it is what it is really is mapping input to output. And the last decade was a lot about optimizing supervised learning. So if you've been in the field for a really long time, like I have, it was really a lot about supervised learning. We had a deep learning boom a decade ago, and now it's all about Gen AI. So the prediction is that this decade is more about Gen AI. And one interesting thing that I wanted to mention is that if a model is small, and we'll see what that means. What does it mean for a model that is small? But let's say if a model is small, what increasing amount of the data will eventually plateau performance, because we say the model overfits, which means it memorizes the data. What we're seeing, and this was true for supervised learning, that was something we really watched out for. That is not true for generative AI. We're not seeing overfitting for generative AI yet. And so the more data we give it, the better performance. So there's a huge difference in performance between supervised learning and generative AI, in that we are not seeing overfitting yet. And that's partly because these models are huge. And so the amount of data that it would take them to overfit is probably quite huge, but we're not there yet. Okay, so let's take a step back. What is a model? And so again, like I told you before, a model is a mathematical representation of a real world system, right? It's a model, it's an algorithm, it's a formula, it's a pattern. Mathematically, it's an equation. And the way I think of them is machine learning models are really big statistical calculators, right? It is just playing with numbers and tuning them the right way. Model components, these are what we mathematically represent things. Again, we're not going to go into too much technical detail, but it's just good to know some of these things. So the Y is the class to be predicted. This is what we're trying to predict. It will be the model output. What we call X is the input data. So these are also called the features. So this is the information that the model will take in to predict the model output. The parameters or the weights are tunable numbers in the model that encode the learning. So we'll see some formulas. And of course, what really matters as well is the model architecture class. So this is the actual formula or equation, and we'll see a couple. And so the model class defines the mathematical formula used. So for example, a linear regression class uses a formula in the shape of y equals ax plus b, where y is, of course, the output class. This is what we're trying to predict. X is the input features. This is what we are, what the information we have. And A and B are the parameters. So these are the weights. And what will happen, we'll see an example of this. What will happen is that the model will try to find the right values of A and B, where if given X, it can predict Y, right? And this, in this way, the way I've written it here, it looks like this is a single column, and it could be. But in reality, this is a series of columns. So this would be a vector. And so it would be y equals, if I would expand it out, it would be y equals a1x1 plus a2x2 plus so on, anxn plus b. Okay. Another example, so if logistic regression, for example, this ends up, this is used when y is continuous. A logistic regression is used when y is discrete. And again, if you don't know what these are, don't worry about it. I'm just trying to show you a little bit under the hood. It's not necessary for the rest of the exercises, but just in case you are interested. So a logistic regression is you take the linear regression model and you pass it through a sigmoid function, which is an activation function. Again, if you don't know what that is, you don't really need to, but the idea is to show you that underneath these systems is an actual mathematical equation, right? And this is the simplest one. So I've put these here because they are the simplest ones. But as models become too big, the exact mathematical equation becomes too complex. And so we visualize their architecture with abstract diagrams. Okay, and we'll see a couple of these. But again, at the heart of it is a mathematical equation. And so these are some of the types of algorithms. We've got linear regression, logistic regression, decision trees, random forest, naive Bayes, support vector machines, SVMs, neural nets. These blue ones are for unsupervised learning, so nearest neighbor clustering and some dimensionality reduction. Again, this is a lot of what predictive ML was concerned with, is choosing the right class of model, understanding what these models do, what is the equation underlying them, where does it excel, when do I use it, how do I optimize it. This is not so much, this is not true, of course, for Gen AI, but I just wanted to show you if we peel one layer up. So we're not going to go into these. I'm using them as an example to explain to you what parameters are and hyperparameters and so on. I do want to go a little bit into deep learning or neural nets because they are the underlying foundation for a lot of things, including Gen AI. So deep learning, the human brain is made of different layers, 6 layers to be exact, of neurons that are stacked. And the way the human brain works is that neurons interconnect with each other. And there's thousands and thousands of connections per neuron. And this is an image from Ramon Cajal, the father of neuroscience. And you can see the layer of neurons. So this is a layer and this is a layer, and how they interconnect. And so neural nets, artificial neural networks, what they try to do is mimic that behavior. And so what you've got here is a neuron. This is a processing unit. This is at its heart is a logistic regression function. And we stack them. So there's a layer here. This is the input layer. And then we've got another layer. So you think of them as you've got layers and layers and layers, and this is it. You've got layers and layers and layers. And this is the first one is called the input layer. The last one is called the output layer. And everything in between is called a hidden layer. And what these are, the connections here, but from neuron to neuron, are what the parameters are. So this is the strength of connection. The parameters, what they do is they encode the strength of connections. Again, you don't need to know that, but we're going to see. So again, I didn't put the formula here because this would be quite complex. These would be logistic regression. So these would be, and then they would connect to each of these. Each of them would connect to each of them. And when I was in graduate school, we did actually write those and we coded them up in Python and so on, but we do not need to do that here. But you're going to see another, so these are the underlying systems, again, that encode transformers and GenAI, but we don't really need to get any deeper than that. So what is a parameter and what is a hyperparameter? So a model parameter is a tunable variable. So this is something that the model can change, and it is internal to the model, and whose value can be learned from the data through training. Okay, and this is what encodes the learning of the model. So two different models that have seen different data would have different parameter values or different weights. Parameters and weights are the same, refer to the same thing. What are model hyperparameters? Well, these are variables that are external to the model. Their value cannot be learned from the data. But what hyperparameters do is that they control the learning process. And so examples of hyperparameters are the learning rate of certain algorithms, the number of epochs, this is how many training cycles the system went through. Regularization, this is a system that constrains the, the model from getting too big. So when you download a model, a pre-trained model, what you're actually downloading are the parameters or the weights of that model. You are not, I don't know that hyperparameters are always included. They don't affect the model performance. But so models are sized by the number of parameters, and hyperparameters are good to keep track of because they might explain, they might allow you to troubleshoot through things, but they're not, they are not important for the actual learned information. They're important for the learning process. Okay. Okay, so solving a supervised learning problem. We went through this in the previous session, so I'm just going to go through it very quickly. And so again, we start with the business. Tech serves the business, and so we always start with the business. We understand the business goal. We try to frame the problem, which means we transform that business problem into mathematical notations. We understand what metrics are great proxies. We plan the process. Then once we do that, we go into the data realm. We collect data, we clean it up, we decide on what our features are, what matters. And then we get into the model domain. So we select a model class. We decide, is this a classification? Is it a regression? What model fits best? You know, am I running a neural net? Am I running an SVM? I don't think anybody runs SVMs anymore, but they were very popular before the deep learning boom. Am I running an XGBoost, a random forest? And so you set that model, you train it, you evaluate it, you optimize it. And then once you're happy with its performance and it generalizes, it's very important that it generalizes well. Then you deploy it and you'll maintain it. Okay. And so what does training a supervised model look like? Well, what happens is that, again, it has the learning itself is encoded in these weights or parameters. What ends up happening is that the model, when you start training, it initializes them at random. So it starts them at random. It makes a prediction. So it says, okay, well, this is in supervised learning, so I know the answer. We know the answer to these instances we're looking at. And so it makes a prediction, and then it looks how far is it from the actual data. It calculates some sort of metric. It could be, we call it an error, but it could be in reality, it's optimizing an objective function. So that could be, it could be maximizing accuracy, for example, or minimizing error. So that the general term is optimizing objective function, but I'm making the assumption here that I'm minimizing an error. And so I calculate the error between the model predictions and the real answers. And then it goes in and edits the weights to reduce that error. And then it tries again. And so what it does is it repeats the cycles 2 to 4 until the error doesn't go down. And I'll show you an example of how this is done in one of the demos. So you start the models, you predict, you calculate an error, and you adjust the models, and you keep doing this until you can no longer reduce the error. Okay. And so I have 3 demos here. I'm going to put them in separate videos. And so I'm going to demo how software is different from machine learning systems. I have a little notebook which I'll release to you for you to play with. I'll also demo this training, how that works with the linear regression, which is a very simple model. And I also want to demo the TensorFlow playground, which I like very much. So I'm going to release those as separate videos. And that's it for this one.